So in this set of practice problems, we were looking at a few different things, looking at calculating the pH of a diprotic solution, diprotic acid solution, calculating the pH of a weak base solution, and calculating the pH of a weak conjugate base solution, and then looking at some strength of how to determine the strength of bases qualitatively. So again, with a diprotic acid, this means that it has two steps in the dissociation of the two protons. So the first step is the dissociation of the first proton, Ka1. The second step is the dissociation of the second proton, Ka2. And if it was a triprotic acid, it would have a Ka3 with it. So as you go from first proton to second proton, the third proton, they get more difficult to remove. So the Ka gets smaller. And so with a diprotic acid solution, and even triprotic, the majority of the hydrogen ions comes from the first step. So if you just take the first step and determine the pH based on the first step, you can get a pH of the solution. And so this is just like you would if you had to do a weak acid pH of weak acid solution. You would do this the same way. So again, this is our dissociation. The first step, we dissociate one of the protons. This is the Ka expression. We do our ice table. Now at equilibrium, you notice the minus X. Well, here the initial concentration of acid is greater than the Ka. And so we can negate this minus X. So now we've negated this minus X, we can set up the Ka expression and solve for X. And so X here is the concentration of Ha minus and the concentration of H3O plus. And so we can get the initial the equilibrium concentration of Ha minus, which is just X, and we can take the negative log of it and get the pH. So the initial pH of this solution is 3.46. And again, we assume that most of the hydronium ion concentration is formed in the first step. Very little hydronium ion concentration forms in the second step because the Ka is so small in the second step. So we found the pH of the solution. We found the conjugate base concentration at equilibrium. Now we need to find the concentration of the fully deprotonated form of the acid. And so for the second step, we have the Ha minus with water. It donates its proton. We get the fully deprotonated conjugate base and a hydronium ion. And again, Ka2 expression would equal this here. So since in the first step, the concentration of Ha minus is the same as H3O plus, in the second step, they're going to be approximately the same as well. So therefore, we can cross out H3O plus and Ha minus, and we get Ka2 is equal to the concentration, the equilibrium concentration of A2 minus. And so there's no need to do any calculations. Whatever your Ka2 is going to be the equilibrium concentration of A2 minus. And if you look here, if the hydronium ion concentration is 3.7 times 10 to the negative 10, when you add it to 3.43 times 10 to the negative 4, it's not going to change much. Because that means, 10 to the negative 4 is on a factor of 1,000,000 times larger than 10 to the negative 10. So adding this to 10 to the negative 4 is not going to change your answer that much. That's why we approximate and say it in the second step, the H3O plus and Ha minus are the same concentration. So now looking at weak bases. So again, Bronsted-Lowry acid base theory, a base accepts a proton, so it forms a conjugate acid. So we want to know what is the pH of a 0.07 molar solution of aniline, and the pKb is given to us as 9.4. So again, pKb is related to the Kb, similar to how pH is related to the hydronium ion concentration. So what we know is that Kb is equal to 10 to the negative pKb. So if we know the pKb, we take 10 to the negative of that, we get the Kb. So the Kb is about 4 times 10 to the negative 10. So now we have that. Next, we need to do our dissociation equation. So here, our weak base aniline accepts a proton from water. We form the conjugate acid and hydroxide ion concentration. And this is what the Kb expression equals. Notice this is different than the Ka because here we have hydroxide ion concentration, whereas with Ka we had hydronium ion concentration. So again, we set up our ice table. We have the initial concentration of weak base. We do the change. We get the equilibrium concentrations. Now here, since Kb is very small compared to the initial concentration, we're looking at an order of a magnitude of 10 to the 8th difference, which is quite small Kb compared to the initial concentration. We can go ahead and negate the minus x. And for most weak-based solutions, you can always negate this minus x because the Kb is going to be a lot smaller than the initial concentration for most situations. So then we set it up, we solve for x, and we get x to be about 5.3 times 10 to the negative 6. Now remember, x is the concentration of the conjugate acid and the concentration of the hydroxide ion. So the first thing you want to do is calculate the pOH. So the negative log of hydroxide ion gives us the pOH. And then once we know the pOH, we can subtract it from 14 to get the pH. So 8.72 is the pH of this weak base solution. So in addition to having molecular species that are weak bases, we can also have anions of weak acids that are also weak bases. Just to kind of recap, for weak bases, you can have compounds or molecules. If it's a compound, it's going to have nitrogen in it. So this class of compounds with nitrogen is referred to as amines. So amines is a class of compounds that have nitrogen in the organic compound. So amines are things like caffeine, nicotine, what else? Amphetamine, dopamine. These are all amines. They're all weak base types of compounds. So that's one category of weak bases is molecules. The molecules are the class of organic compounds called amines, which are derivatives from ammonia. Ammonia is the most simple, is the simplest amine you can have. And then the other category is the anions of weak acids. And these occur as salts. So for example, fluoride, bromate, bromate, hypobromate, nitrite. These are all anions of weak acids, so they're weak base solutions. So here we want to calculate the pH of potassium of a 0.008 molar solution of potassium hypobromate, and it gives us the pKa of the weak acid. So again, when you're looking at this, what we're interested in is the anion. We don't care about the potassium because, as we'll learn later, potassium doesn't affect the pH of the solution. So when you see a salt and you're looking for a weak base, the weak base component is going to be the anion of the salt. The potassium, the sodium have no effect on pH. And so what we know is we need to find the pKb from the pKa, and then we can find the Kb. So we know that pKa plus pKb equals 14, just like pH plus pOH equals 14. So we know the pKa, we can subtract it from 14 and find the pKb, so 5.3. And again, the lower the pKb is, the stronger the base, just like the lower the pKa is, the stronger the acid. or I should say, the stronger the conjugate acid is for lower pKa, the stronger the conjugate base is for lower pKb. And then once we find the pKb, again, 10 to the negative pKb will give us the Kb. So here we have the Kb of hypobromite. Now, whenever you're dealing with a solution involving an anion, a weak base anion, you're never going to find the Kb. You're always going to be given the Ka or pKa of its weak acid counterpart. So now we put up the dissociation. Again, here, this is a weak base. It accepts a proton, forming the conjugate acid and hydroxide. We do set up the ice table, the change, equilibrium. Again, the Kb compared to the initial concentration is a lot smaller, so we can ignore the minus x. Now we can solve for x, and we get x to be 2 times 10 to the negative 4. Again, this is the concentration of hydroxide and conjugate acid. We take the pOH, we find it's 3.7. But don't stop here, that's the pOH, so we have to subtract it from 14 to get the pH. So the pH of this solution is 10.3. So now we get to the good stuff, identifying strong bases, strong acids. So bases are kind of the opposite in criteria than acids. So in a previous lecture, we talked about acids, finding the strongest acid. Now we're going to look at finding the strongest. Of course, these are all weak bases, but strongest, weakest base. And these are all types of amines. And so again, we're going to use the same acronym that we used last time, except we're going to go forward. So now we're going to start with the H, then go to the I, and go to the R, and then E. Again, these for bases a little bit more loosely. It's not as concrete as the acids, and you'll see why when we look at some examples. And so with bases, we want to look at the hybridization of the nitrogen atom. So if you remember back from the, taking Gen Chem 1, we have different types of hybridization, sp, sp2, sp3. So for acids, acidity increases as you get more S character. So the more S character your hybrid orbital has, the more acidic it is. Likewise with bases, it's the opposite. The more P character your hybrid orbital has, the more basic it is. The basicity increases. And so when we're looking with bases and they're all amines, or they're all, we're looking at weak bases trying to identify the strongest one, the first thing we need to look at is the hybridization of the element that's going to be accepting a hydrogen. So in all of these, it's the nitrogen. So we want to look at the hybridization of the nitrogen in each one of these. So you look at the nitrogen here, it's sp2. Here it's sp3. Here it's sp2. Remember, you count double bonds as one group. And here we have sp3. So based on hybridization, the more P character the hybrid orbital has, the more basic you could say the nitrogen is. So based on that, we can go ahead and cross out A and D, because those are sp2, whereas C and B are sp3. So now we got two choices, sp3 for B and C. We want to know which one of these two is the stronger base. And they both have the same hybridization. So let's go to the I, which is in the inductive effect. And so here, if you remember with acids, we looked at electron withdrawing groups. So the stronger the electron withdrawing, the stronger the acid is. But with bases, again, we look at electron donating. So what we're looking at is which molecule is pumping electron density into that nitrogen atom to make it more lucrative, more negative for a passing proton passing by. And so here in B, we have 2 methyl groups and a hydrogen. But in C, we have 1 methyl group and we have 2 of these big, bulky ethyl groups. So these 2 ethyl groups, along with the methyl group, are all pumping electron density in to that nitrogen. And the reason this is important is because you're pumping electron density into that nitrogen. You're making it more negative. You're making it more attractive to a proton. So the more negative it is, the easier it's going to grab a proton and become the conjugate acid. And so since C has 3 alkyl groups and B only has 2, and the other group is a hydrogen, C would be the stronger or strongest weak base out of these 4 given. So here again we have a series of 4 compounds. So here we have 4 compounds. And you'll notice that some of these have nitrogen, so they're amines. One is a anion, so a conjugate base of a weak acid. Well, they actually all are. And so in all of these, the reaction center is going to be the place that can accept a proton. So in 3 of these, it's nitrogen. And in 1 of these, it's an oxygen, single bond oxygen. Now, you may say, well, oxygen's more electronegative. It's going to be more negative. But with this here, you got to remember that this oxygen, there is resonance in the structure. So what that resonance does is it spreads out this negative charge. So even though this is an oxygen, and oxygen is more electronegative than nitrogen, and we'll get to electronegativity in a second, but since there's resonance, that's going to cause this negative charge to be spread out over 2 oxygens. So it's not going to have the full potential of just 1 oxygen atom having negative charge. It gets spread out between the 2. So B would be the weakest base here because, again, it has oxygen. Now, if you remember from acids, the element, we said if the elements are on the same, what's it called? The elements are on the same period, the more electronegative elements is going to be the more acidic. If you remember, we talked about that when looking at the higher acronym. Now for bases, it's the opposite. It's the lesser electronegative element is more preferred for bases than the more electronegative element. So everything you learn for acids is the opposite for bases. So just remember that when you're looking at bases here. And so if you notice, all of these nitrogens are sp2 hybridized. And again, there's a nitrogen here. So they all have the same hybridization. This oxygen has resonance. We're not going to include that because that's going to be one of the weaker bases. And so in all 3 of these, we have sp2 carbons. Now you see here with A, we have methyl groups. C, we have a fluoro group. And D, we have 2 nitrogens. We know which one of these would be the strongest base, strongest weak base. And so you should probably already kind of know that the one with fluorine would not be the strongest, because remember, fluorine is electron withdrawing. So what's happening is it's removing electron density from the nitrogen, making it less negative. So if you make something less negative, it's not going to be as attractive to a passing proton to get attracted to it. So electron withdrawing groups actually minimize the effect of the nitrogen. So then we're left with A and D. Now you may say, well, D, there's two of them, that should be better. But what happens is when you have two of them, they're both competing. So they're both playing this tug of war between each other for the electron density. So therefore, it wouldn't be as strong as, say, A, which has one nitrogen, and you have these methyl groups pumping electron density into the nitrogen, making it more lucrative. And then the more electron density that nitrogen has, the more negative it is, the easier it can acquire a proton. And so for bases, it's the ease in which it can acquire a proton makes it a strong base. So the more negative you can make that reaction center, the easier it can acquire a proton. And so A here would be, out of these examples, the strongest weak base. So again, with acids, we want something to withdraw electron density to keep the reaction center, keep that hydrogen, making it easier to break off, because if there's less electron density around the oxygen, the hydrogen can remove easily. However, with bases, we want a base to be very negative so it can grab on to a proton very easily. That's why they're opposite of one another. And then lastly, just to kind of help with previous sessions, we have these acids, and we want to rank these from strongest to weakest. And so what we're going to do is, again, we're going to look at the higher principle. And just to let you know, I didn't come up with this. Someone else came up with this, and it was very good when they told me, so I like to use it. So with acids, we're looking at the elements attached to the acidic proton. So for A, it's attached to an oxygen. D is attached to an oxygen, and E is attached to an oxygen. Now, if we look at, for example, B, butane does have an acidic, it can have, in theory, an acidic proton, which is attached to a carbon. And then butane also has a hydrogen attached to a carbon. So in theory, it could have an acidic proton. So C and B, the acidic proton is attached to a carbon. A, D, and E, the acidic proton is attached to the oxygen. So automatically, we know that C and B are going to be the weaker end of acids, because again, they're attached to a carbon, and carbon is less electronegative than oxygen. So we'll come back to B and C in a second. Now A, D, and E, they both have, or all three of them have, this carboxylate group. So they all three have resonance. So we have the same element, the same degree of resonance. We got to look at the inductive effect. And so now if we look at A has no electron withdrawing or donating groups. A D has an electron donating group. This methyl group is pumping electron density back into the reaction center. And E has a nitro group, which is electron withdrawing. So out of all three of these, the one with the electron withdrawing group would be the strongest. Now between D and A, the one without the electron donating group would be the next strongest. Because when you're pumping electron density back into the reaction center, that oxygen is holding on to that hydrogen a little bit more tightly, making it harder for it to pop off. So D would be 3. Now we get to B and C. So for the higher principle, E, the element, both of them are attached to a carbon. R, resonance, there's no resonance in either one of them. I, inductive effect, there's no electron withdrawing or donating groups attached. So then we get to the hybridization. And so this is the hybridization of the element attached to this acidic proton. So here, this carbon is sp hybridized. And here, this carbon is sp3 hybridized. And if you remember from the previous slide, I forget which one it was, but the more S character in your hybrid orbital, the more acidic that proton is. So the more S character in your hybrid orbital of the element attached to the proton, the more acidic that proton is. So in that case, C would be number 4 and B would be number 5. So again, we use this higher principle to help us evaluate the relative strengths of the acids. Now this again is a qualitative way of qualitative determination of the strength of acids.